Okay, so welcome to Focus Private Tuition. So in this video, we're just going to continue with what we were talking about. In the previous video, we looked at rate and collision and what you can do to measure rate of a reaction. We also looked at how you can determine order, the rate equation, graphs, rate concentration graphs, concentration time graphs. We looked at many other things, but here's in addition to all that information, we want to talk here about other things pertaining to reaction kinetics. We want to talk about something called activation energy, which here is the minimum amount of energy that is required for a reaction to occur. Remember what we said when we talked about successful collisions and unsuccessful collisions? We talked about energy, and we said for particles to react, to collide and be able to successfully form a product, they must collide in the right orientation with the right amount of energy. So now comes in activation energy, which is the minimum amount of energy that you require in order for you to have a successful collision. So let's look at this. Remember what this is called? That's called an energy profile diagram. So what's going to happen here for this particular reaction, you have your reactants at a higher energy level. So this is the energy level showing on the y-axis. And we see that as the reaction progresses, you're going to form your products which are at a lower energy level compared to the reactant. So remember, this is a typical energy profile for a what? For an exothermic reaction where you release energy. So we need to know how to represent your activation energy on such an energy profile diagram. So remember here, so from this stage to the peak here, your molecules will be absorbing energy. So you would have expected maybe that we just move from here downwards in a straight line, but actually this is what happens. So what's happening from here to the peak of this curve, your molecules are absorbing energy, and when they get to the peak there, so that's the energy gap, that's the activation energy that they are absorbing. And you need to remember it's always between your reactants and the top of the profile. So from here to the top, this is where your reactants are actually absorbing the minimum amount of energy that is required to kickstart the reaction. So it's always between the reactants and the top. Okay, so we are saying here at this point, the top, the bonds, they have sufficient energy to break. So for reactions to take place, in most of the cases, you're breaking bonds, old bonds, in order to form new bonds. And bond breaking is an endothermic reaction that requires energy. So this is the energy that goes into breaking those bonds. Okay, so this is your activation energy on a typical exothermic reaction energy profile diagram. Okay, okay, so we looked at that. So reactions that have a low activation energy need less energy to break the bonds, normally heat energy and vice versa. So if your activation energy is low, that would be good, because the reaction will take place with a minimum amount of energy input. So let's talk about something called the Maxwell Boltzmann distribution curve. So Maxwell Boltzmann distribution shows the energy in gas particles. So here's the thing. Particles of a gas in a sample move at different speeds. Some move slowly, some move quickly. They have different amounts of kinetic energy. Okay, if we plot this on a graph, we get a Maxwell distribution, Boltzmann distribution curve. So here's the typical curve. So you can see its shape here. So what does it tell us? So the graph is starting at 0, 0, where there's no particles have kinetic energy. So it's starting at 0 number of particles with kinetic energy. So everything is starting at 0. Okay, so here's the thing. This top part of the graph is showing us the largest number of particles in this graph contain relatively this amount of energy here. So if you're going to sample a particle, take any particle randomly from this sample, its likely amount of energy is going to be around this level, because this is where you find most particles. This is the amount of energy where you find most of the particles. Okay, and then there's this, which is the average energy of the particles. So it's going to be around this level, slightly higher. Okay, and somewhere near the end here is where you find your activation energy. This is where you find your activation energy. So you can tell that a lot of particles have less energy than the activation energy. So these particles, especially these to the left of this blue line, have very little kinetic energy and they move very slowly. So remember that the particles need to move fast enough in order to collide with other particles in order for us to have those successful collisions. So quickly, we're going to be looking at factors that affect the speed of a reaction. And you're going to realize that the kinetic energy of these particles is very important. So this is a typical, the typical distribution of energies amongst particles in a gas sample. So most particles move with round about moderate speeds because their energies is between this here, where you find most of the particles, and the average energy of all the particles in that sample. So all this is telling us that a lot of particles have low energy than what the minimum amount of energy that is required for a reaction to take place. Okay, so and then we have a small proportion now of particles with activation energy or at activation level, and beyond we have a small amount of particles. Okay, so what affects rate? So temperature, the particles on average more kinetic energy. They have more kinetic energy when they are heated. So if you heat, you are going to increase this proportion of particles that have enough activation energy in order for them to collide and react successfully. So your temperature, if you increase temperature, it's going to change the shape of your Maxwell Boltzmann distribution curve, such that you see that a small proportion has been added to the proportion of molecules that contain enough energy to react. So this is how temperature will alter the shape of your graph. It's going to move slightly higher at this point here, thus increasing the proportion of particles that contain enough energy to react. So this will overall increase the speed of your reaction. Okay, so remember that the curve shifts to the right here, and the peak is lower and the area under the curve is the same. However, the area under the curve beyond activation energy increases. So this is temperature, how it affects. Then when we decrease temperature, this is what would happen. The curve is going to shift to the left. The peak is now higher and the area under the curve still remain the same, but the area under the curve beyond activation energy decreases. So this is the effect of temperature according to Maxwell Boltzmann. Other factors, so why do we have a faster rate? We are saying here the particles move around more at higher temperatures and they collide more often, and hence the reason this is the reason why the reaction happens faster. So the particles are now moving faster. Okay, all right. Concentration and pressure also affect the rate. So increasing the pressure increases the rate of reaction. The particles are closer together and collide more often. There are more frequent collisions and a higher chance of a reaction. So this is the illustration here. When you have high pressure, you have more collisions. All right, concentration acts in a similar manner to pressure. Increasing the concentration increases the rate of the reaction. The particles are closer together and collide more often. There are more frequent collisions and a higher chance of a reaction or successful collisions taking place. Okay, catalysts. Now we come to this other factor. So a substance which increases the rate of reaction by providing an alternative pathway that is a lower activation energy. So this is important for you to understand on a graph. Let's go to the graph. There are different types of catalysts. We're going to come back to this. We want to look at how your catalyst is going to affect. Let's come to this. So a catalyst, what it's going to do, it's going to provide an alternative pathway. Look at this. So this is the pathway without a catalyst. This is a pathway with a catalyst. So you can see that the amount of activation energy has been reduced. So this causes, so when we go to the Maxwell Boltzmann distribution curve, look at what has happened. Our activation energy has been decreased to this level, and in turn this has increased the proportion of particles that contains enough energy. So we're going to continue from here in the next video. You might want to go through the factors, how they affect the speed of a reaction. So I'll meet you in the next video.